All right, well, Kevin, I greatly appreciated your presentation on CFD, and I appreciate working with Cornell and on CFD as well, but I find myself still promoting states into moving from the 1D. So it's quite impressive that Caltrans is using CFD, quite honestly. I think you guys are really stand above many. But so the main focus of my presentation is to continue to promote the use of two-dimensional hydraulic modeling, and in this case specifically for scour. So as you can see on the right side here, especially for complex hydraulics, multiple opening bridges, the use of one-dimensional modeling really just does not give us a good representation of flows. We make a lot of assumptions when we use 1D modeling for that type of application. But first, you may have all heard of this acronym floating around, CHANGE. Well, what is CHANGE? As you can see, it's spelled out here, but it's part of a Federal Highways program called Everyday Counts, which is basically a program, Federal Highways, to help promote underutilized technology. And basically, it gives us an opportunity to help states make this transition from 1D modeling to 2D modeling. We've been providing supplements for training. We've been developing a lot of new resources, essentially. And that's part of in my presentation, I want to share some new things that are coming out to help support scour analyses in 2D modeling. But first, I want to highlight a couple things. This is maybe kind of a broken record, but I keep coming back to the fact that we started promoting the use of 2D modeling for scour and complex bridge hydraulics in HEC 18 in 2012. Okay, so it's nothing new. We're just getting more resources now to help states make this transition. But again, you see a lot of highlights here talking about, anytime there's skewed embankments to the flow, multiple floodplain openings, wide floodplains, highly contracted flows. You'll see I've crossed out FST 2DH. We have transitioned to the use and recommendation of SRH 2D. But basically, anytime you have a complex flow situation, we're strongly promoting the use of 2D modeling. Now, if you think you have a simple bridge, take a closer look. Okay, I'd say most bridges fall in the case of complex flow categories, all right? So just kind of keep that in mind. But let's look back at some of the considerations, I would say, or assumptions for 1D modeling. It's surprising to me sometimes how some of these folks don't even think about or realize. Some of them are obvious, like flow direction. Okay, when we put together a 1D model, we assume flow direction. Okay, when you draw a cross-section, it assumes perpendicular to the flow. When you lay out the flow path in a 1D model, you're telling the model that's the flow path. And do we always know there's only one? Or do we always know the direction? You also assume the contraction and expansion through the bridge opening. Flow distribution across that section, each cross-section, is based on available conveyance. Okay, a 1D model does not preserve continuity in the overbanks. Okay, that's key when it comes to flow through multiple opening bridges. That's a big one. A lot of folks don't think about that. They don't recognize that. In a 1D model, flow may be over on one side, in one cross-section. All of a sudden, you open conveyance on the other side, it can magically just get distributed. And that's just so continuity is not necessarily maintained. Again, velocity is assumed in one direction. And a lot of people like this velocity distribution plot they can get out of a 1D model. And quite honestly, we've relied on it too much. They don't realize that velocity distribution will always give you the highest velocity in the deepest part of the channel. Okay? It's not accounting for momentum, all right? And so it's made up from one-dimensional average velocities. Okay? And some other assumptions here, so we'll get into those. Now, when we move on to 2D modeling, all of these things are computed. Okay? Flow splits and multiple flow paths are directly computed, so you get a much more accurate flow distribution. All right, so this is very important when we're looking at multiple opening bridges. Okay, if we can't accurately assess flow through each opening, how can we accurately assess scour? Okay, something to think about. So again, it computes the flow direction. We now have velocity vectors to know several things. We know where that flow starts to get contracted in the main channel. So in other words, we can help that to assess where an approach cross-section is. And we also have a computed flow direction upstream of every pier. We no longer have to guess. All right. We also have a more accurate water surface elevation for determining overtopping flow when that incipient overtopping occurs. and also when we have pressure flow. And beyond that, there's several advanced tools that we currently have, and we have some new tools coming that I'm excited to tell you about. So first of all, when I talk about tools, we do recommend the use of SRH2D, that was written by Dr. Young Lai, who's in the audience with us today. And we're also using a custom graphical interface developed by Aquaveo, and Dr. Alan Zundel is with us today as well. And both of those merged together are the tools that I'm talking about here and recommending. There's ongoing developments coming out here soon. And I do want to emphasize that there is a free community version available to everyone. All right, this does not necessarily come at a cost. So just to give you an example here, this is from New Hampshire. What I have here is you're looking at a 2D model result for velocities, but overlaid on that are the 1D HEC-RAS cross-sections. A couple things I want to highlight here is that if you start upstream to downstream, you see some of these recirculations here along the sides. And again, those things you'd never pick up in a 1D model. It doesn't account for that ineffective flow area, essentially. But also, you'll see this is a fairly straightforward flow split. Okay? And so as we go down here through the cross-sections, and you'll see, at this last cross-section here, and even at this upstream face of the bridge, in a 1D model, it, again, is just going to distribute flow based on the conveyance area you give it. It does not know how that flow got there. Much different in a 2D model. So in a 2D model, we can see all the flow vectors. It is computing the flow distribution, preserving continuity and momentum as we go through the domain. Okay, a big difference there. And if we're going to look at a cross-section now, right at this section here at the upstream face or upstream edge of the embankment. And I tried to scale these. We've got a 1D HEC-RAS output and then the SRH2D output. Most of you are probably familiar with this plot with the velocity distribution. On the bottom, I have a similar plot with SRH2D and SMS. You've got the ground surface, you've got the water surface, and then this red line is the velocity, and that corresponds to that right axis. A couple things to highlight here is that, realistically, you look at the difference in velocities. The maximum velocity shown in the 1D distribution here is 7.4 feet per second, whereas in the 2D model, it's 8.6. Doesn't seem too different, 10%-ish or so. Look on the other side, again, 7.5 to 7.6. That looks pretty close. Okay, but again, you start to look on the bottom, this higher velocity is maintained over a greater part of the channel. And even when we put out water surface in these two cases, it's the same Manning's end value for both the 1D and 2D model in this case. The water surface varies a little bit. It's not significantly different, not really anything of note. But what I want to highlight here, when we look at the conveyance or the discharge, it's, I wouldn't say significantly different, but this is a fairly simple split flow case. And the discharge differences here between a 1D model and a 2D model are upwards of 15%, 10 to 15%. Okay, and now I intentionally didn't use a very complex project. So hopefully the lights are going off where, think about what impact this would have on your scour calculations. And again, so if we could use 2D modeling to come up with more accurate assessment of the flows and the velocities, ultimately it is going to give us more accurate scour calculations. Okay, so let's talk a little bit more what tools we have available. So now we're telling you to do this in a 2D model. How do you extract these values? So currently in the SMS package graphical interface, you can simply draw arcs. And in this case, man, I want to walk when I'm stuck here behind the microphone. In this case, when we're drawing the approach section, this is always something that has eluded many in a 1D model. How do you pick that approach section? Okay? Technically, that approach section should be upstream of the bridge influence before you start to see flow diverted from the overbank and into the main channel. That is fairly challenging in a 1D model, okay? Especially considering you're making all these assumptions on flow distribution. So in a 2D model, it's much simpler. You can observe the flow vectors, and at the point where you start seeing flow diverted back to the main channel, you want to go upstream of that. And then we want a width of flow, essentially representing the width of flow that's transporting sediment. Okay, most commonly, we use top of bank to top of bank or toe of slope to toe of slope. In a 2D model, again, you can look at critical velocity and use that as a guideline and a lot better indicator. But we draw that approach section, and then it's a lot easier. We can draw a section at the contracted location, and we can generate summary tables. So the summary tables produce our discharge, our width, our average velocity, average unit discharge, and we can copy those, paste those in a spreadsheet, or enter those into the hydraulic toolbox. So that's out there now. Many of you maybe have been aware of that and using it. Okay. I wanted to highlight this. So this is what the summary table looks like. Anytime you draw an arc in SMS, you can specify, do you want the main channel or do you want the overbank flows? You can specify minimum, average, and maximum values for all the variables it generates. Again, so it's quite helpful. You get the flow and the width. So it has much more application than just Scour. Okay, and here's another tool. So there's a data calculator, we call it, in SMS. I'm going to credit Will Darasat at Ayers Associates for thinking of this. It's pretty useful. If you take the critical velocity equation in HEC 18 and rearrange it, you can come up with a critical velocity index that we can enter in the data calculator in SMS, and basically, assuming a single D50 for the entire domain, identify what's mobile and what's not. Okay, so you can use this to assess clear water scour or live bed. Okay, and again, looking at some of these things graphically, it's very helpful when trying to assess scour. All right, so new tools. This is what's coming soon. Coming soon to a SMS near you. But so SMS 13 is going to be the new version. And Alan tells me it's on the horizon in the coming weeks. So let's say a month. But so these tools are coming. And initially it is going to be released in beta version. We do need some testers to make sure we get all the bugs worked out. But basically what it's going to do, this is going to include a new scour coverage. And the goal here is help to standardize the practice of assessing scour to try to get some more consistency in how people select the approach section and how they extract variables. And so it's going to involve the user creating a center line for reference, drawing this upstream approach arc, okay, with some guidance. But again, you have the vectors to look at that. And if you need to, you could actually look in alternate locations and see how sensitive it is to it. You then draw a section across the contracted section here at the bridge. You identify bank locations, both at the approach and contracted section. You draw arcs to represent the pier length and alignment. You specify the width, identify the abutment toe locations, and basically hit go. And then what it does, it computes all the appropriate values for contraction scour, abutment scour, and pier scour, and it extracts those and pastes those into the Federal Highways Hydraulic Toolbox. Okay, and so at that point, the user then, well, in fact, I've got, well, before I go to the next slide, I want to highlight a couple things. You can see a couple of the key things. It is computing, you can see the little arcs drawn here. It is determining that approach angle on each pier. Okay, so you're no longer eyeballing that. All right, so it's directly computing that. Now, you do have to take in mind that channels migrate over time, but this is very, very helpful to assess the current situation. All right, so it's going to take all of those variables, extract them, and just a quick highlight here from HEC 18, all of the equations we're interested in. Basically, we're looking at depths, discharges at the approach and contracted section, widths, again, depths, unit discharges. Those are the variables that it's extracting, and then paste those in the hydraulic toolbox. Now, many of you maybe have already used the hydraulic toolbox. We've got several calculators, so the user has to pick what methods what you want to use for contraction scour and abutment scour and so on. Okay, so that's all still there, but what we've added, and this is, by the way, I'll give you a link to this. It's on our hydraulics page. There's a new version of the hydraulic toolbox that's been posted. It is version 4.4, and it now includes this scour summary table. Okay, the key here is that when you one thing I did not mention, when it's SMS is extracting all the variables, it's also extracting the channel geometry, the pier locations. Okay, and you still currently have to identify the deck elevation, but that's coming. You can also do this still from HEC-RAS as well, from a 1D. Okay, so we've added this feature. So once you add the geometry, we can now take all of the components and produce this summary table. Okay. And then with that, it also has a Scour summary plot. It's been around for a little while, but we'll continue to improve it. So here's some resources for you. If you've not been on our hydraulics page, you certainly should Google FHWA hydraulics. There's a software page and a training page to get to some of these resources. These aren't posted yet, but they will be coming soon. A couple things I also want to highlight. There's some bridge scour tutorials that we're working on that follow these methods. As soon as we have those available, we'll post them on the website. We'll make sure states are aware of it. We are very interested in states, again, following the right steps. I think, Brad, you mentioned earlier that sometimes HEC 18 is a little hard to navigate through, so we're trying to help improve that. My cohorts and I are also working on some Scour webinars that we want to put out there to help states and others understand the methods better. If you haven't taken the 2D course from NHI, certainly I recommend you look into that. A couple other things here. We do have some advanced training you can look into as well, some web-based training. YouTube videos. I didn't give you the link. It's just easier to search on FHWA, SRH2D. Okay, and bi-monthly, if you want to stay in the loop on all this, bi-monthly I do a webinar. Everybody's welcome to attend. If you're interested, just email me. And, oh, there's my email at the end, but let me try to show this slide. I had one closing slide, the future of bridge scour. So we are doing everything we can now to help folks transition to 2D modeling. To give you a little idea of our vision, you've heard all of the work that's going on at the lab with Scour and the research. Argonne's been doing a lot, and they've got a very good handle on computing local Scour and CFD model. Our vision and where we're working towards is to work with Dr. Lai and integrate the ability to predict local Scour in a 2D model. Okay, we're not there yet, but just to kind of give you that idea, that's where we're heading. So this is a CFD model just showing where they're at. And there's my contact information. So if there are any questions, that's all I have. Stay here. Yeah, Burke.
Scott, do you think it might be possible to take the CFD research and use it towards developing like our informing peer scout or local scout?
Oh, absolutely, absolutely. And all of the research, there indeed will be tech briefs coming out to update HEC 18, as was alluded to. As soon as we can, we're taking that research that, between what's going on in the lab, what's going on in our CFD modeling in Argonne, and as soon as that's ready to hit the streets, we'll be updating our procedures. But it does take time. But everything that the lab's working on, we're trying to get everybody up to 2D modeling speed so they're kind of ready for new stuff. So this is all going to come together at some point. Great question. Others? Yeah, Dave.
Yeah, I overheard some discussion about using different N values for 2D modeling versus 1D. Do you know anything about that?
I do. There's been lots of discussion. The question of what N value is, I've actually seen presentations at different conferences suggesting different N values for different 2D models. Those presentations weren't based on any calibrated data. I think most of us have done modeling. We know that there can be a difference. A 2D N value is most often could be less than a 1D model, just because in a 1D model there's a lot more lumped into it. I personally have seen differences up to 10%. I've heard numbers of 20 to 50% thrown out there. I'm not supporting that at this point, but certainly there's talk of even putting a research statement together for that. So the strongest recommendation there is to calibrate your model. Other questions? All right, well, one more.
For the upcoming version on the pier scour equations, is there a radius around the pier it's using to determine velocity and angle of attack inputs?
So the question is for the tool that's in SMS, as far as the values that it extracts, it's based on the current pier scour methodology. For the current pier scour methodology, it uses the approach velocity, so upstream of the pier, approach velocity and depth. And technically before that drawdown starts occurring. So really it's, you go up a distance, and we've got some values sent, say roughly one bridge deck width upstream. It's in that range. So it's, you want to be upstream of the influence of the pier to measure that approach velocity and depth. Does that answer your question?
Yeah.
Okay, so that's what the SMS extracts and pastes into the Hydraul Toolbox. Great question. Is that it?
Anyone else?
All right.
Thanks.
Thank you all.